And right now we're back to our slide. So this is another example here, and basically this is a rigid disk. This disk its mass equal to m, and its moment of inertia about, say, the center is O, okay, about the center O equal to IO. We know when we talk about the moment of inertia, that means we have to talk about which point respect to we talk about, because respect to the different locations that the the value is different, okay. And basically here, this kind of the disk rolling on a surface. Say here, we're assuming there's no kind of slick there, so basically there's no relative motion between the sphere, between the disk and the ground. Okay, otherwise we will have additional considerations. So here we're taking the degree of freedom as the SEQ, and here we want to calculate equivalent mass. So equivalent mass, basically, again, we starting from is this. The whole system will be described in terms of the kinetic energy is equivalent mass, and multiplied with here is our degree of freedom SEQ. So let me say SEQ dot square, okay? So that is such an equivalent description. So right now, respect to these original systems, we have to dig out the components, how many components played in describing the kinetic energy. So from here you can see this disk kind of rolling onto the surface. You can see it's moving, translating, also it's rotating, spinning by itself, right? So from here, dynamics, you should right away, the kinetic energy should come in from the translational energy and rotational energy, two portions. So translational energy is the movement of the center. And right now you can see this one actually is rotating in terms of the theta omega here. Okay, so let me use this one. So this is the degree of freedom theta. So basically, say the radius is r. So right now we know that the r times theta equal to x, and that is the kind of compatibility. Basically, that is the relations between the rotation and the translation, because we assume there's no relative motion here, so this right away form. So right means the r is rigid, is constant all the time. So we take the derivative is something like this. Okay. So right now we have two components: kinetic energy due to translations, and that is mx dot square. And actually x, we're taking this one, x should be xeq, and this is the degree of freedom. Okay, so then we put the xeq. So this is eq here. The second portion of the kinetic energy is due to the self-spinning. Okay, and self-spinning, that is basically is I-O respect to the dot square. Okay. So from here, you plug in this relation here. So basically, the theta dot equal to that one. So therefore, here we basically, this one is always equal to m times I-O r square, and r square times xeq dot square. Okay, so that is okay. So therefore, the equivalent mass simply is equal to this term. Okay, and if you still remember a little bit when you learn dynamics, basically for this vibrating, for this kind of rotating system, you can visualize actually this disk is rotating about this point. under that situation, it's basically the entire kinetic energy of this disk. If you describe respect to this point, and then we call it A, so basically the kinetic energy will be equal to 1/2 times I respect to point A times theta dot squared. Okay, so you can go back to look at your textbook. Actually, this term is equivalent to the whole term here. Okay, they are equal. So that means I moment of inertia with respect to point A actually equal to this term. IA will be equal to, in this way, IA will be equal to IO plus MR squared. Sorry, should be like this. Okay. So that you can also use the simple properties of the moment of inertia. You can also achieve the same result. But here, I simply using the one method here. Okay. Yes.
I'm afraid I don't quite follow your algebra. Right, you got to
this one?
No, the one above it.
This one?
Yeah, it's circled in red.
Yeah, and let me try to do it again. Okay, so so from here, this theta dot, and plugging here is equal to xeq dot divided by r, right? And then we simply take the IO divided by r squared, come out to this one. You good?
Yeah.
Okay. Any other questions? No? Okay. So this is another example. I forgot which one is which one, but this is similar to the homework. And we have such two examples here. Let me work on this one and leaving the other one to you. So here we want to calculate the MEQ respect to the degree of freedom. Here we assign our degree of freedom x to the displacement of this block. Okay. So here we using the displacement of this block as our degree of freedom. And if you wish, you can also assign the degree of freedom to the movement, to the displacement of this one, or assign to the rotation, the angle of this kind of spring, either way. As long as you assign, and eventually your equation of motion will be equivalent to other people using the different definition of the degree of freedom, because this is a single, this is the first degree, this is a single degree of freedom. And so basically your equation of motion will be the same. And here, for this case here, we assume this bar is rigid. Okay, that bar is rigid, basically that working as a level. So working as a level, that means all the points on this bar, their displacement will be related to each other. For example, the displacement on the top here can be related to the displacement at the bottom here. I'm going to do it right away. So let me work on this one. So this is a rigid and no mass. Okay, so say this is the degree of freedom, and you can pay a little bit of attention here. I'm going to show you a tip and the way of analyzing the system to get something information. So I follow the defined degree of freedom. So here, follow this direction. I'm going to assume in the same direction. So that means I'm assuming this point going to be displaced to here. You see the displacement of this assumed displacement basically aligned to whatever we are given. So that is my exercise. Okay, and then if this point displaced to here, because this is a rigid, so the whole thing will become a kind of straight line, but simply pivot at this point. So that means that is the, okay, so this is a pivot point here. So that representing is the displaced configuration of these systems. So such that this point is x. Okay, that x is our degree of freedom, and respect to which we're going to determine MEQ and KEQ, etc. Okay, because this is rigid, so who can tell me what is this number? Again, this is a level. So all the points in the level can be related. You simply using triangle. So let me plot the triangle. So using the two triangles here. So this is a triangle 1, and this is another triangle. The two triangles must be similar using this relation. So that means, let me call this is what we want to calculate and say whatever. Let me use this one. That one, respect to this length, A, will be equal to in similarity of the triangles, and will be x and respect to B. So this one you can see right away, this one basically equal to A over B times x, right? You good? Good. Yes.
Questions. So we're just assuming that there's no like vertical movement of the levers.
Nah, yes, that's a very good question.
Don't worry about it.
Yeah, that's a very good question. Another assumption in any for 0,8, in addition to assuming that everything is linear, we also assume small oscillations. So small oscillation, that means, say if we would have a sine theta, then it can be approximated by theta. If we have a cosine theta, then that can be approximate as equal to 1. And for example, say, that's a 1. Small oscillation, that will make sure the system deform won't be too big. Otherwise, additional nonlinear term will be coming out. We don't touch this one at this moment yet. Okay. So again, in reality, this movement will be kind of the arc. But for kind of small portion, we assume that is still horizontal segment there. That's a good question.
I have a second question. So what's the J naught term that's given on the graph?
Yes. Sorry, my mistake. I think for this example, we need to consider mass. So no mass is moment of inertia. My mistake, sorry. About the pivot equal to J now. Thank you. Okay, so with everything, then we can begin to calculate. So the first one is we're going to determine is MEQ. So with everything ready, so we can say for the equivalent systems, and for the equivalent system described is 1/2 MEQ multiplied with the degree of freedom velocity square. So that is this one. Okay, that is our equivalent description. And that should be equal to whatever the original system. In the original system, how many initial terms we have, initial objects we have? 3. 1, 2, and this one. This one has the rotational mass. Okay, so from here we're expecting 3. So that is 1/2 from this term is m1 times velocity square. And what is the velocity? M1 has a displacement equal to that one, so A over B x dot. We good? And plus the second term is 1/2 the M2. So right now we finish this, and I'm going to fix this one. And this one is moving in terms of x, and that is x dot square. And the last one is due to the contributed by this length here. So the last one is 1/2 times J, using the symbol here is JO. And JO is a rotation, is a moment of inertia, and that is going to spin about this point. And let me say this point is, this one is theta. Okay, what is theta? So basically that is theta dot square. And what is theta dot? theta, if you look at this geometry, theta equal to x divided by b. Again, we assume the small. So again, if that is the kind of we know from the one arc of the circle, say if this is the radius is r, and the arc length say is x. Okay, so basically this theta equal to x over r, right? And the same thing, because we can just approximate, this is a portion of that kind of arc. We do the approximation. Okay, so we take this one. So therefore, theta dot equal to this one. So plug in everything. So therefore, from this side, MEQ will be equal to M1 times A over B squared plus M2 plus JO divided by B squared, and that is MEQ. Okay. And the next exercise I want to determine is the KEQ. So in the next page of the slides, and we let me keep this one. Good. Okay. So basically, the next one I want to calculate is the KEQ. So how to determine KEQ using the same example here. So let me. Well, can I erase this portion? Is it good? So for determining the KEQ, again, we're using the equilibrium of the moment or force. So, or you can utilize the conservation of the strain energy. Maybe you can use the conservation of the strain energy. So from the equivalent, the description, that is K times X squared. Okay, that is the strain energy from the equivalent system. Again, we describe in terms of designated degree of freedom systems. So now for this system, how many springs here? 3, right? 1, 2, and 3. This is a spiral spring. Okay, so from the first spring is 1/2 times K1 and times the displacement square, and displacement is A over B over X. And for the second spring, and that is 1/2 K2 times displacement, which is X squared. And the third one is the spiral spring. Spiral spring has this, here is called the KT, so it's not very clear. Let me call it KT. And KT, the spiral spring is such that the spring constant multiplied with theta squared. Okay? So basically the KT have, for example, the K1, K2 has a unit something like the the newtons per meters. Okay? So KT would have the is Newton per the radian, whatever the different. But basically, what I want to say, the KT and the K2, K1, they have a little bit different units. Okay, so under this situation, what is theta? Again, theta equal to these, using that information, x theta equal to b. So theta equal to b, b theta equal to x. Okay, so theta equal to x over b. So plug in this information. So this one simply equal to x over b. So therefore, KEQ will be equal to K1 A over B squared plus K2 plus KT divided by B squared. Okay. So for the same systems, we already have the MEQ. So the system will be equivalent to this one, KEQ, and then MEQ, and then the degree of freedom is x over t. So if I were ask you what is the natural frequencies of this system, so basically the natural frequency of the system simply is KEQ divided by MEQ. Okay, you plug in whatever we calculated for equivalent spring, and from the previous page for equivalent mass, then you can determine the omega n. If we are given any numbers, then you can begin to do the calculations here. Good? If okay, then the next, yeah, for people you can catch up the writing here. For this one basically is, I believe that is similar to one of your homework, this one. So let me skip out the practice in class and let you work on this one. Okay, so this one, it won't be hard. Again, this is the rigid level, and in the similar fashion, it has a moment of inertia JL with respect to the pivot. So using the rigid level, right now is L-shaped. And you should be able to figure out the relation between the displacement of this, which is our degree of freedom, to the displacement of this point, which means at here. Build up this relation and then begin to formulate using the equivalent kinetic energy for MEQ and using equivalent spring energy for KEQ. Very similar process to we just did it. Okay, give it a try. So that one we have done already. So let me skip on this one. So right now I want